Okay, so now that we have our predicates, we could use them instead of propositions to make formulas, exactly the same way as we made formulas out of propositions using logical connectives. We could also do a few things that you will see in a bit that we couldn't do with propositions. So here are some examples. If we have a formula even x or divides 3x, which means 3 divides x, implies that x is not prime, this formula may be true or may be false depending on the value of x. And in this formula, everywhere x means the same number. So when we instantiate it, when we put in some value, we will put the same value everywhere x occurs in this formula. So suppose we put in number, I don't know, 5. Then 5 is not even not divisible by 3. The whole thing must be true, because false implies everything. What if we put in 3? Or 2? Well, in this case, in this scenario, something else happens, because, for example, even of 2 is true. So even though 3 does not divide 2, we got something true before the implication, and then we need, for the whole formula to be true, the x not prime to be true, but 2 is prime. So therefore, the whole formula will be false if we put x equal to 2. But it's true if we put x equal to 5. So for such formulas where we have x just floating around, ready to be replaced with whatever we want, we call such x a free variable. We are free to replace it with any value of the domain. For example, in the second formula, where we have a different formula and a different x, here x means some person, we could put in a name of somebody who is a feminist and a bank teller, and it will make the formula true. Or we could put the name of somebody who may be not a feminist, even though they're a bank teller, and the formula would not be true. It will be false. So this, together with a little bit more stuff that we will see in the next lecture or two, is called predicate logic, as opposed to the propositional logic we did so far. It's the same kind of connectives, but now we are using predicates instead of propositions. So let's see what kind of other things we could do in predicate logic that we didn't do in propositional. So first of all, you probably have seen some kind of theorems, and chances are they look like this. For every something or other, the following is true. And then you will have some kind of statement which has a variable for which you said for all, whatever, for all x as a free variable. For example, it would be something like for all x that are integers, if 6 divides x, then 3 divides x. Or for every natural number n, if n is greater than 4, then 2 to the n is greater than n squared. Now in the predicate logic, we have the special symbol, special notation to write things like that and actually make the whole sentence like that into a formula. And for that, we will use quantifiers, which will quantify our variables. And by doing that, the whole formula will get a truth value, well, provided there are no other free variables floating around, possibly changing the value of the formula. So for example, the first quantifier that we encounter is the universal quantifier, which we write as this upside down A, and usually we will read it as for all. So for all x that are integer, if 6 divides x, then 3 divides x. For all n that are natural number, if n is greater than 4, then 2 to the n is greater than n squared. So now we got a formula with no free variables, and we could look at this formula and with a little bit of work, prove that it's true, prove that it's false. We could talk about the whole thing. There is no variability anymore, and we have no control over x anymore, because we want our formula to be true in this case, no matter what kind of value of x we put in, as long as it comes from the domain of x. So let's look at some examples. Suppose we have a sentence, every bird can fly. So now we are talking about birds. So our domain could be birds, and we could have a predicate can fly. So our formula says for every x in the domain of bird, it's true that x can fly. Okay. So one thing about propositional and predicate logic. Surprisingly, you will find that especially predicate logic and quantifiers are a good exercise in self-awareness. Yeah, right, logic teaches you self-awareness. How in the world? Well, the way we just did this, every bird can fly as a formula, is by listening to ourselves saying the sentence, every bird can fly, and trying to understand on another level what is it that we are saying. Okay, we are saying every. Aha, every means all. Aha, we know how to write for all, for every. Now, what kind of things are that every corresponds to? Okay, every takes values that are all birds. Okay, so our domain is birds. And what is that thing that can be true or can be false about objects from our domains, about birds? Well, that's whether that bird can fly or whether it cannot fly. So you see, by listening to yourself saying the sentence, every bird can fly, you can convert it into a logic formula. Let's try this exercise again. By the way, is this formula true? Well, think of penguins. Okay, suppose you say, oh, I work every day of the week. Now, how can we write it as a formula? Let's listen to ourselves saying it. I work each day of the week. Okay, each, kind of like every, it's kind of like all. So it means for all days of the week I work. Kind of the same thing. So what is our domain? We are talking about days of the week, so our domain will be days of the week. What is our predicate? Do I work or do I not work? This is what can be true or can be false on any given day. So we will have a predicate work. We are not talking about anybody except for me. So the only thing that varies here is that x in the days. Do I work on Monday? Do I work on Tuesday? So we will have a predicate work, which takes a parameter x, which can take a value of the day of the week. And now we could write a formula. For every x in days of the week, work of x. Is it true? Is it false? I don't know. Maybe true for you, sorry, or maybe false for you. Maybe you have fun some days. Okay, let's try something else. Any two people are related. Okay, now our domain is people. Our predicate is related, and related is a predicate that takes two parameters, not one. And because we don't want those parameters to be the same, we will give them different names. We will call the first one x and the second one y. Now we could replace x with the name of one person and replace y with the name of a different person. So now we could write bigger looking formula for every x from the domain of people, and for every y from the domain of people, related xy is true. By the way, sometimes when we use the same kind of quantifier and the same domain, we could just put the name of the quantifier, then list variables, and then put in the domain. For example, for every xy in people. And then we could use our formula, in this case, related xy. So let's look at some more examples. So now we will have a little bit longer formula. Before, we really only had formula that was the name of the predicate and nothing else. But let's look at every integer is either even or odd. Again, listen to yourself saying this sentence. Every integer. Every means all, so for all x's that are from domain of integers. And what are our predicates? Well, that x is either even or odd. And that's exactly what we could say, even of x or odd of x. So for every x in integers, either even of x is true or odd of x is true. Here is another example. Adding 1 to any odd integer results in an even number. Okay, this one is slightly more complicated to parse because you have the tricky word here, any. But in this case, you could also say it adding 1 to every odd integer, or for all odd integers, adding 1 to it results in an even number. And now we could write it as a formula. And as you see here, in even, instead of x, I put x plus 1. And this is an okay thing to do because even takes values from the domain of integers. And if x is an integer, then x plus 1 is also an integer. So it is okay to replace whatever variable it is in even with x plus 1. So for every integer x, if x is odd, then x plus 1 is even. Okay, let's try every odd integer as prime. Again, every integer, but now we are talking about odd integer. So how would we write it? One way to write it is to make odd as a domain, but sometimes it's kind of inconvenient because we would be throwing a lot of things into the domain. Let's for now make our domain integer and phrase the sentence a little bit differently. Every integer, if it is odd, then it is prime. So now we could write our formula using predicates prime and odd for every integer x. If odd x, then prime x. So again, the trick here was that other than making the domain all of odd integers, which we could do using a set of all odd integers as a domain, instead we set our domain to be integers, but said if it's odd, then it's prime. So let's try something talking about more numbers. For every two numbers, one is less than the other. Well, we're talking about numbers, and really it could be all sorts of numbers, but let's say real numbers. That's general enough. So let's say our domain is real numbers, and the predicate that we are using is less than, because we are talking about one number is being less than the other. And rather than writing less than of xy, we will just write x less than y the way you usually do. So for every x in real numbers, for every y in real numbers, either x is less than y or y is less than x. One is less than the other. Either the first less than the second or second less than the first. So let's now look at those formulas and decide which one of them is true and which one of them is not. So the very first one, every integer is either even or odd, I think it's true. Because every integer, the way we define it, is either divisible by 2 or that integer plus 1 is divisible by 2, so it's either even or odd. The second one, That's also true. If you have something odd, you add 1 to it, you get something even. Every odd integer is a prime. That's not quite right because 9 is odd, but it's not prime because 9 is equal 3 by 3. And finally, for every two numbers, one is less than the other. Okay, now it's tricky, and here it really matters how we interpreted less than. Here we interpreted it as strictly less than the other. But what if we make x and y to be the same? Then 2 is not strictly less than 2. And if you turn them around, 2 is still not strictly less than 2. Therefore, the whole thing will be false. So notice that x and y can take, each of them can independently from each other take any possible value from the domain. And nothing stops them from being equal or being not equal or really being whatever they want. And universal quantifier tell us that no matter what they take, the formula should still be true. In this particular case, if they take the same value, the formula is then neither x less than y or y less than x will be true if they're the same, and so the whole formula will be false. So let's try to kind of formalize what we just did. So for every formula which has a free variable x, we could make a formula for every x in its domain, f of x is true. By the way, here, f is a formula of predicate logic, so nothing stops us from having a formula x which has its own quantifiers on different variables. So x is free, but maybe f starts with for all y, like we just had in the last example. And oftentimes, if something is of this form and there are no more free variables, we will call it a universal statement. Universal because it starts with universal quantifier. So now, how do we determine whether something is true? Well, an expression of the form for every x in the domain S f of x is true if and only if for every element a in the domain, f of a is true. That is, if your domain consists of element a1, a2, a3, and so on, then for all x in S, we could just write as f of a1 is true, and f of a2 is true, and so on and so forth, and for all the elements in the domain. And then we will get an equivalent, though much longer formula. Sometimes we cannot do it. Sometimes we talk about things like numbers, and this expression will end up being infinite. So having a universal quantifier is a really useful shortcut. And in general, as we just did, to figure out whether a universally quantified formula is true or false, we just need to check that for every possible value of x, the f of x would be true. Okay, so let's try an example of evaluating a universally quantified formula using this technique of writing a formula which is the end of the original, where the variable is substituted by all possible values in the domain, and checking whether the resulting propositional formula is actually true or not. So, because we want something small, let's take the domain to be just 3 elements, 3 numbers, 0, 1, and 2. And let's take familiar predicates x less than or equal to y and x greater than or equal to y. So notice that here I'm using less than or equal and greater than or equal, so they're going to behave a little bit better, a little bit nicer than the strict less than that we saw in the example. So let's take the formula for all x in the domain of 0, 1, and 2. X is greater than or equal to 0, and x is less than or equal to 2. So we want to show that the formula is true. And for that, we are going to replace x with all the possible values in the domain and take end of the resulting formulas. So the first we will have 0 greater than or equal to 0 and 0 less than or equal to 2. That's when we set x to be 0. The second part is when we set x to be 1, 1 greater than or equal to 0 and 1 less than or equal to 2. And finally, 2 greater than or equal to 0 and 2 less than or equal to 2. All of them are true, so the whole formula is true. And therefore, the original formula, which says for every x out of 0, 1, and 2, this expression is true, that's also true. Okay, let's try something else. What if we do for every x out of 0, 1, 2, for every y also out of 0, 1, 2, x is less than or equal to y? Let's show that it's actually false. So first we will take this formula and we will write it out just for the x as a quantifier. So we will treat for all y x less than or equal to y as just a formula. So this is what we get. Our original formula is equivalent to an AND of 3 formulas, each of which is the result of taking the formula, removing the for all x quantifier, and replacing x in the first case with a 0, in the second case with a 1, and in the third case with a 2. So we get an AND of 3 formulas, just like we had above. So now let's do the same thing with the for all y quantifiers. So now we just treat each of those for all y in the domain something less than y as a separate formula. Let's write it out. So the first one becomes 0 less than or equal to 0 and 0 less than or equal to 1 and 0 less than or equal to 2. So far, so good. But if we do it for the second possible value of y, for y equal to 1, we end up with 1 less than or equal to 0. So wait a moment. Now we got something that is not true anymore, and we put an AND with this thing, so the whole formula will become false. We found, counterexample, we found a place where the formula doesn't hold, and since the formula, since the quantifier says it has to hold everywhere, well, we found a place where it doesn't. Actually, there are 2 more such places, because if we write out the third formula for all y 2 less than or equal to y, there will be 2 places where it's false, 2 less than or equal to 0 and 2 less than or equal to 1. But you know what? The moment we found one place, that's enough for us to say, no, it doesn't hold everywhere. So this technique works nicely when we have very, very small domains. And as you can see already, even for the domain with 3 elements, we ended up with a formula which consisted of 9 different pieces, pretty long. But when we have domains that are infinite, when we have numbers, integers, real numbers, then we cannot quite do it. We need something else. We need proofs of a different kind. And we spend a fair bit of time in this course later on talking about the ways we could prove universal formulas like that.